This following video, we're going to discuss absolute and relative change, percent increase and decrease. So keep in mind, a percentage is a portion out of 100. Percents are going to be really important in this section. We're going to talk about the differences between the percent of something and also talk about the use of percentage in percent increase and percent decrease. Before we get to percent increase and for percent decrease, let's talk about two important concepts, absolute and relative change. So oftentimes we're really interested in how something is changing as it goes from one point in time to the next. And so if we think about values as having a new value and an old value in terms of time, then we can calculate absolute and relative change in the following way. Absolute change is just the total change as something goes from one value to the next. I like to refer to that as new minus old. So if I had $30 in my pocket yesterday and I have $40 in my pocket today, then the absolute change is a positive $10, right? Absolute change can be positive or negative. Of course, it's positive if something is increasing over time. I had $30 in my pocket yesterday and today I have $40. It's increasing by $10, so my absolute change is positive. But if I had $40 in my pocket yesterday and $30 in my pocket today, now the role of new and old are changing, and I would have a negative $10 as my absolute change. The negative is telling me that I lost money over time. Then we can talk about the idea of relative change. Relative change is calculated as new minus old, all divided by old, times 100. And I put that times 100 in here because when we calculate new minus old divided by old, the answer that we get is a decimal. And so relative change is often expressed as a percent. And so when we multiply by 100, we're turning that into a percent change. Let's look at some examples of relative change. The first example says in 2000, UNLV's enrollment was 22,043. In 2017, the total enrollment for UNLV was 30,471. Find the absolute and relative change in UNLV student enrollment. And so the absolute change, which I'm just going to refer to as ABS, absolute, is going to be the new value minus the old value. The later one in 2017 is the one I'm going to refer to as, quote, new. So we're going to go 30,471 minus the old value, 22,043. These are commas, not decimal points. And when we make that calculation, $34.71 minus 22,043, we get 8,428 students. Again, don't forget to put your unit on these. So it's a total of an increase of 8,428 students over the course of those 17 years. And we want to look at the relative change, which I'm just going to refer to as REL. And the process is pretty similar. 30,471 minus 22,043, all divided by the old value, 22,043. And when we do that, I'm going to take that number and multiply by 100, and I get 38 point, and now it just kind of runs on 2, 3, 4, 3, 6. So I'm just going to estimate it at a one decimal place after the percent. So I'll call it roughly 38.2%. Again, I would specify what you need to round to on relative change if it doesn't come out to be a nice, neat number. When we're looking at real life data where this problem actually came from, most of the time it doesn't come out to be a nice, neat number, and it's our responsibility to round relative change. More often than not, I will have you round relative change to one decimal place after we express it in percent. And so we can see that the enrollment at UNLV went up 38% in those 17 years. Let's look at another one. According to the website Statista.com, 943 million music CDs were sold in 2000 in the United States. Awesome. In 2016, 99 million CDs were sold in the US. What's the absolute and relative change for CDs sold in the US? So the important thing to keep in mind in this problem is that we're having this decrease, right? In 2000, the early value or the old value, we have a large number, 943. But of course, with the advent of downloading digital stuff, CDs, physical CDs weren't as necessary, and so we can expect to see the new value to be much smaller. We should also expect our absolute and relative change to have a negative value attached to it. So let's find out our absolute value first. Again, new minus old would be 99 minus 943. Remember that this is in millions, so at the end I can put million CDs to take care of all those zeros. 99 minus 943 is going to give us negative 844 million CDs. And the relative change is going to be 99 minus 943 all over the old value 943. So we get I'm going to round to one decimal place again. I get negative, don't forget to multiply by 100 so that we can turn this into a percentage. And we get negative 89.5%. Or you could say like this, or you could say an 89.5% decrease. Either one of those would be appropriate. And as expected, the sales of CDs just kind of fell off when in between the years of 2000 and 2016. I assume this year it's even lower than that by a lot. So now that we've talked about absolute and relative change, we want to talk about some other important ideas with percentages to keep in mind. The first thing I want to talk about is the difference between these statements that I have here. Of a number and increase or decrease. These mean different things when we're talking about percentages. And so what we're looking at with relative change is an increase or a decrease. What we were looking at in the last video with part, percent, whole, those are percentages of a number. We have a part and a whole, and that percentage is representative of that ratio. But this idea with relative change is taking percentages and kind of applying a new role for them and saying, okay, in terms of a percent, how much are you growing or how much are you decaying or taking away from one value to the next? So it's important that we talk about those differences and make sure that we know that those differences exist, and when we're looking at a problem, which one we're looking at. When we're given a portion of an entirety, we're talking about these first ones up here, of a number. But when we're talking about a value that changes over time, where we can assign a new value and an old value, this is when we're talking about an increase or a decrease. So this page right here is really, really good. I definitely recommend just printing it out and keeping it with you in the beginning as you're working on part, percent, whole, and as you're working on relative change, just to kind of get an idea of how percentages are working. So, of course, 100% of a number means that that value stays the same. If I have 100% of the candy bars that I'm supposed to sell, then I still have the same amount that I started out with. There's no change there at all. 100% of a number. A percent smaller than 100% of a number means that we're looking at a portion of a whole, right? 45% of students are enrolled full-time. We have a whole, which is the group that is enrolled, and then we have a 45%, a smaller portion of that whole. That's the group that I'm talking about that was enrolled full-time. A percent of a number that's larger than 100 means that the original value has increased. So I still have 150% of the candy bars I'm supposed to sell for the fundraiser, means that I started out with, I don't know, 20 candy bars, and now I have even more than that. I got 20 plus half of that. I got 30 now. And so this one kind of explains that. Gina got sick, so now I have to sell some of her candy bars too. Now remember that those part and whole pieces, we talk about percentages of a number. Now we're going to talk about the next examples. We're going to talk about increase of a percentage or decrease of a percentage. So if you have something and it increases by 100%, then that would tell you that the original amount doubled. And an increase of 200% means the number tripled, and so on. An example could be going back to candy bars. If I have 20 candy bars and I increase the number of candy bars by 100%, that means I got another 20 candy bars laying around, and now I have a total of 40 candy bars available to eat or sell. I'm that kind of guy that if I have a fundraiser, I'll just buy all the candy bars myself and throw them in the freezer and just eat them myself, because I know I'm going to eventually eat that much chocolate, so why not? So an increase of a number that's more than 0% but less than 100% indicates that an original number is an increase, but not enough to double it. Again, I kind of talked about that with the other value. Oh, let's do an example of candy bars again. If I have an increase of 50% and I started out with 20, then I can take this 20, I can multiply it by 50%. And we did this with the Jack Jack toys in part percent whole. I can multiply this by 50%, which gives me 20. But because it's an increase of 50%, I need to take this 10 and I need to add it back to the original amount, which tells me that an increase of 50% in this particular problem was taking something that was 20 and now it's up to 30. A change of 0% means that the number stayed the same. If I had 20 candy bars originally as my new value and my old value was 20, I'm going to take all of this and I'm going to throw it into the relative change formula. And what you'll see is that you get exactly 0% change, right? If I went from 20 to 20, I didn't grow, so I shouldn't have a positive relative change. I didn't decrease any. I don't have a negative relative change. I just got 0% there. Then a decrease of a number between 0 and 100 indicates that the number is falling, right? And so we're going to talk about how we calculate those here in just a minute, but I'm going to use that same example of candy bars. Let's say I have 20 candy bars to start and I want to decrease by 50%. I could take that value of 20, multiply by 0.50 again. Here's my 10, but because I'm decreasing, I don't want to add this 10 to the 20. I want to subtract it. And so I started with 20, I decreased by 50%, and now I have 10 bars left. A decrease of 100% means that I lost everything, right? If I had 20 candy bars and I sold 100% of them, I have no candy bars left. And then lastly, a decrease greater than 100% cannot happen, because if I only have 100% of something, then I can't lose more than that, right? If I have 20 candy bars, there's no such thing as me losing 150% of those candy bars, because I only have 20 of them to lose. So I can't lose 30 if I only have 20. That leads us to a really important concept when we're dealing with markup and discount, or percent change, I should call it, percent increase and percent decrease. And so I like to refer to percent decrease and increase and decrease as finding the multiplier. Increase and decrease is in terms of percent are always relative to 100%. So a good way of explaining that is if I want to increase by 20%, for example, what I'm going to do is I'm going to start out with my 100%, and because I'm increasing, I'm going to add 20% to that, which gives me 120%. And then, because I'm talking about this idea of a multiplier, I take this percentage and I express it as a decimal. And so 120%, again, if we want to express a percentage into a decimal, then we just divide by 100, and this gives us 1.2. This is our multiplier. A multiplier is really powerful because what it does is it allows us to apply a percent change very, very quickly. So now I could say something like an example I'm just going to make up here real quick. I'll do the one that I just did. I have, well, let's do 200 candy bars. And then I increase by 20%. We just found that the multiplier for increasing something by 20% is the same thing as 1.2 for the multiplier. So what I do then is I just take my 200 and I multiply by 1.2. And when I do that, I get 240 candy bars. What the multiplier does is very similar to what we did in the end of the last lecture and in the very early part of this one with the Jack Jack toys, where we found a part and then we added it or subtracted it to the original value. But what this does is it allows us to do that in one step. Instead of taking 20% of 200, which is 40, and then adding that back to the 200, finding that multiplier allows us to just make that connection very, very quickly. This becomes even more important when we're doing percent decrease. So now that we've looked at an example of finding the multiplier, I'd like to just write out a couple examples of finding the multiplier and have you work on them on your own. So I'm going to write out a few examples and I want you to give me the decimal representation of those. So let's look at a couple here. How about we just did an increase of 20%. Let's do an increase of 45%. We'll do an increase of 250%. And then we'll do a decrease of 10% and a decrease of 60%. So on your own, try to calculate all four of these values in terms of the multiplier or the decimal representation of these. And again, you can just pause the video when you're ready and pause it. An increase of 45% would be 100% plus 45%, which is 145%, as a decimal 1.45. An increase of 250% would be 100% plus 250%, which is 350%, as a decimal, that is 3.5. So in other words, a 250% increase of something is the same thing as multiplying it by 3.5. A decrease of 10% would be 100% minus 10%, which is 90%. And 90% as a decimal is 0.9 or 0.9 or 0.90 if you want to put the 0 in the end here. And then lastly, a decrease of 60% we could say is 100% minus 60%, which is 40%. And 40% as a decimal, 0.4 or 0.40. Now that we know how to work the multiplier, it'll be really useful in the problems that we're looking at here. So let's look at one. I'd like to look at this one here. A sweatshirt that is normally $55 is marked down 20%. What's the sales price of the sweatshirt? Well, we want to first find out how to discount something by 20%. So we know we start with 100%, we're going to subtract 20%, which means if it's 20% off, we're buying it for 80% of the cost. As a decimal, 80% can be thought of as 0.8 or 0.80. Now that we have our multiplier, we just need to apply this to the original value to find the new value. Normally, it's $55. Now we're going to take this value and multiply by 0.80, and that's going to give us $44 as the new price. Let's look at another one. In the 2008-2009 academic year, UNLV charged $129.50 fee per credit. In the current academic year, the same fee has increased by 73%. How much is the fee now? So we have a 73% increase, which we know is 100% plus 73%, 173% as a decimal, 1.73. This is our multiplier. We want to multiply this value by 1.73. And we go back and we identify what the old value is. And the old value is $129.50. So 129.50 times 1.73 does all the math for us in one step. And we get rounded to the nearest cent. Don't forget to always round to two decimal places. $224.04 is our new value. So now, in more a general way, we can say we have a relationship between the multiplier, the new value, and the old value. It turns out that the old value times the multiplier is equal to our new value. And the cool thing about this relationship is it fits very well on a triangle, just like part percent whole did. We put our old value here. We put our multiplier here. I'm just using MULT. And our new value goes on the top. In the problems that we've just looked at with multiplier, we've always been given the original value and then some kind of percent change so that we can find the new value. But what if we wanted to go the other way? For that, I'm going to actually look at this example. Sorry, they weren't in very good order. In the highlighted example we have here, it says after taxes, the total cost of the latest smartwatch was $572.64. If the sales tax rate is 8.25%, how much was the smartwatch before tax was added in? So we don't know the old value. The old value is the cost of the watch before tax. In other words, we have this watch, then we added 8.25% to it, and we got the new value, which was $572.64. So we need to figure out how to work the multiplier. The sales tax rate is 8.25%. This is always an increase, right? When you go to buy something, the sales tax is added on to the cost. And so our multiplier here is going to be an increase of 8.25%. So to calculate that multiplier, we're going to take 100%, and to it, we're going to add 8.25%, which gives us 108.25%. Don't forget, we need to divide that by 100 to get our multiplier, 1.0825. That is our multiplier for this problem. So anytime that you want to add tax to something, you multiply it by 1.0825, and that will apply the tax on it right away. This can be really, really useful if you have a certain amount of money in your pocket and you don't want to go over it, but you're not sure how much tax you're going to pay, right? You can use this process to kind of work backwards to figure out how much you can afford. Now remember, according to our stuff here, we know that we want to take the new value and we want to divide it by the multiplier in order to get the old value. And so in this problem, we're going to take 572.64 and we're going to divide by 1.0825. And when we do that, we want to round to the nearest cent. I got like 528, 997, and so on. So when I round, I'm actually going to round all the way up to the nearest dollar. 529 was the cost before taxes. So the difference between this and what we were talking about with part percent whole is that these problems, I can't just take the 8.25% and subtract it from the original value, because the 8.25% was applied to this number right here, and that I didn't know going into the problem. That's why we have to find that multiplier and identify which is the new and the old value and attack it like this. Now I have one more that I want to do, and that is going back to section 7 and looking at the Jack-Jack problem one more time. Remember in the Jack-Jack problem what we were doing. We started out with 3,500 toys. Then we had an increase of 25% to get ready for the holidays. And then we had a decrease of 85% because we sold a bunch of that material. So we're going to go 3,500 times, always multiplying with the multiplier, an increase of 125, an increase of 25% is 1.25 as a multiplier. A decrease of 85% would be 15% left over, or 0.15. And what I'm going to do now is I can take care of all three of those in one step. I can take care of the original value, the increase of 25%, and the decrease of 85%, all in one calculation. So 3,500 times 1.25 times 0.15 is going to get us back to where we were before. And again, we can't have a quarter of a toy, so we're just going to round this to the nearest toy. 656 toys, just like we got in the last version of this problem, but significantly faster. So there's a couple other ones in here that I'll leave for you. Again, markup and discount is going to be something definitely covered in your first exam, something really, really important. So practice using this multiplier process. It's a good way of understanding how the percentages are working, and in most problems, it'll save you a step or two once you get comfortable with it.